All right, so I believe this is lecture number 9 for distributed energy resources, and we're going to be talking about heating, ventilation, and air conditioning systems. And I think this material follows pretty naturally from the material on thermal modeling of buildings that we did the last couple of lectures. So we will start by talking about heating, talk about electric resistance heating, kind of the simplest form of electric heating, and then we will talk about electric heat pumps, something that I do some research on. We'll talk about air conditioning systems, which is kind of, once you know about heat pumps, an air conditioner is kind of just a backwards heat pump. We'll talk about considerations for sizing heating and cooling equipment. So, if you know kind of what the energy consumption or the heating need for a house is, how do you decide how big the heat pump or whatever should be? And then I'll show some pictures basically just of some common configurations of heating and cooling systems. And we will wrap up by talking about some simple models of thermal distribution systems. So forced air systems and then hydronic or water-based heating and cooling systems. Let's see. I guess I just want to note that very often the examples that I give you guys in the homework problems are for residential buildings. And often when I'm talking through, the thermal modeling stuff that we did over the last couple of weeks, I would often say like a house or an apartment or something like that. But really all this material that we're learning applies equally well to commercial buildings, things like office buildings, educational buildings, medical facilities, and so on. So a lot of the same ideas, basically, it's just, different scale and different choice of parameter numbers. So in particular, some of the HVAC stuff that we talk about in this fourth section will be more oriented toward commercial buildings and industrial buildings, whereas other parts of it will be more kind of residential. Okay, so let's start out by talking about kind of the simplest form of heating with electricity, which is just electric resistance heat. So very simple. Basically, this thing here is just a hunk of metal, typically maybe something like a nickel chromium alloy. So particularly, carefully chosen metals, but basically just metals. They might have a ceramic core, or it might be metal all the way through. And the idea is you run current through this thing, and via what's called Joule heating, the same effect that we talked about when we were discussing sort of low voltage versus high voltage electricity transmission. Um, Via Joule heating, basically, we get a transfer from electrical energy to thermal energy. So here is a system diagram of what that looks like. So we have an input of electrical work, so P in kilowatts, and then we have an output of heat transfer or thermal energy output. And if we do a steady state first law balance, so conservation of energy balance on the system, where here we'd be drawing the system diagram around kind of the hunk of metal here and the resistor, we find that the input work is just equal to the output thermal energy. So in reality, these things do not always operate in steady state. So if you take a cold hunk of metal and then you start running current through it, first all the metal will warm up and then it will begin to sort of bleed heat into the surroundings. So you'd have to take into account sort of the capacitance, the thermal capacitance of this thing, and that might delay the sort of steady state by 30 seconds or something like that. But anyway, this is a pretty good model. Basically, the electricity in equals the heat out. And you can define what's called the coefficient of performance for the system, which we'll talk about more in the context of heat pumps and air conditioners. But here it's defined basically just as the heat transfer output divided by the work input. And so very simple calculation, P is equal to Q, so this ends up being 1, or very close to 1, 95, 98%, something like that in practice. And if you want to understand, how much current is flowing through or what the resistance of the hunk of metal might be, you can use the formula for Joule heating, which basically relates the heat transfer output to I squared R, where I is the current flowing through the resistor and R is its electrical resistance. So kind of nice thing about resistance heating is that it's super simple, basically no moving parts, extremely robust, and it's super cheap. You don't need a complicated machine. You just kind of need a hunk of metal. The downside is that it's pretty expensive to run, so not very efficient. So if we want a more efficient form of heating with electricity, we move to what's called the heat pump. So here's a picture, a similar schematic for a heat pump thermodynamic cycle. This is probably old hat to a lot of the mechanical engineers in the room, but folks from other backgrounds, this might be new or anyway worth refreshing. So here, basically, we're drawing kind of a generic system boundary that would include all the kind of components of the heat pump machine, whatever it might be. We have an input, again, of our electrical power, electric work, P. And then there would be a heat transfer input from some colder region. And this could be, for example, the outdoor air. And then there would be a heat transfer output to a warmer region. And this could be, for example, the indoor air. So the point of this machine is to deliver the heat transfer output Q out. So if we again do a steady state first law conservation of energy balance on this thing, we add up the inputs, the P and the Q in on the left-hand side and set them equal to the output of the system, the Q out. And we can again define the coefficient of performance. It's just defined here as the kind of the point of the cycle, the heat transfer output, divided by the costly input that we have to inject, and that is the work. So it's Q out divided by P. And then we can use our first law energy balance, solve for P and eliminate that. And then we can divide through everywhere by Q out, and we get this formula here for the COP, 1 over 1 minus the ratio Q in to Q out. And then there is a fundamental performance limit that comes from the second law of thermodynamics, or the law of incursive entropy. And this is called the Carnot performance limit, named after a French engineer called Sadi Carnot, who I think came up with these ideas around 1800 or a little bit before. And this says that for any real machine, the actual COP that we really achieve in practice can be no bigger than this number on the right-hand side. And this basically the formula looks the same as what we have up here, except we replace the Q's by the T's. So Q in corresponds to the temperature Tc of the colder reservoir where we're absorbing energy. And then TH corresponds to Q out. So TH here is the temperature of the reservoir that we're delivering energy to. And then when using this formula, it's important to note that both the cold and the hot reservoir temperature should be in a thermodynamic temperature scale, like the Kelvin scale or the Rankine scale. So here's what that Carnot COP looks like as a function of the temperature ratio, Tc divided by Th. This is the thing that shows up on the right-hand side here. So let's see, Tc divided by Th equal to 0 basically means that the numerator here, Tc, must be equal to 0. So that basically says that we're trying to absorb energy from something that's really near absolute 0. So that's super duper hard. And in that case, basically, we get no advantage from being able to absorb thermal energy from that cold reservoir. And the COP reduces to the same COP that we would have for an electric resistance heating element, which basically just takes the input work and converts it to heat transfer directly. So we get COP of 1. And then in the other extreme, if this ratio Tc by Th is equal to 1, that means that the boundary temperatures are approximately equal to one another. And in that case, the Carnot limit blows up, and in fact, it goes to infinity. So if you plug in 1 here for this ratio, we get 0 in the denominator, and you can get sort of arbitrarily large efficiencies. And then in between, it has this kind of curvy shape. So one way, if you kind of want a quick and dirty approximation of the actual COP of an actual machine, would be to get a sense for what percentage of the Carnot COP your real equipment can deliver as a function of the boundary temperatures. And then you get a curve like this, but just sort of shifted downward in the y-axis. And so a real practical machine that you can build or buy might only get maybe 20 to 30%, something like that, of the Carnot limit. So it might have the same sort of shape, but shifted way down. Okay, so that is the theoretical limit. Let's talk about how you might realize that in practice. So you just need a magical gnome, and then it's really easy to build a heat pump cycle. No, this is an illustration by, I guess you'd call her a climate artist named Nicole Kellner. And she actually drew this based on a tweet that I did, like the first ever viral tweet that I did a long time ago. But this actually was used in a podcast, and I put the link to the podcast on kind of the list of outside sources. So this is about a 45 or 50-minute podcast, I think. And it talks about heat pumps more generally, but they talk about the sort of gnome analogy here. So anyway, the idea is that a heat pump is kind of like a gnome with a bucket that runs around in circles. Outside here, he wrings some heat out of the outdoor air, fills it up in the bucket, comes inside, dumps it out, and then gets tired over time, so needs to sort of eat some electricity to keep up his strength. So subsequently, there was an XKCD comic about heat pumps called "Manual Heat Pumps Are Such a Pain," that walks through, I guess, if you had an accordion full of some ideal gas, air, or something like that, how you could do a heat pump, a manual heat pump. And actually, I don't know if Randall, the artist who draws XKCD, listened to that podcast. I think probably not, but I like to imagine that he did, and that the nerdy quote inspired this comic. But anyway, so let's think through how this works. Okay, so the person running the manual heat pump here, we begin with kind of a lukewarm indoor temperature. And they've got a compressed, I guess, accordion with some kind of gas inside of it. And it's at the same color, which color here corresponds to temperature. So it's at the same temperature as the indoor air. So the person walks outside. Okay, now they've still got this warm stuff here. They allow that to expand. So it would do some boundary work on the surroundings or on the person. As it expands, it cools down if it's an ideal gas. And so here, dark blue means like really cold, and blue means pretty cold, basically. And so now we have a super cold working fluid in pretty cold outdoor air. And so there will be a heat transfer input. So even though it's cold outside in the middle of winter, say, we would still absorb some thermal energy because this is warmer than this. So we would get some conduction or convection heat transfer into the working fluid here. Okay, then they take the accordion full of now warmer gas, go inside, and then they do some work on the system to really compress it. And as it's compressing, the gas then heats up a lot. So red means really hot. So it's warmer than the environment here, and then it basically bleeds heat, again, via radiation, convection, whatever it might be, into the indoor air. So now the indoor air is warmer, and the cycle repeats. Now that, of course, is a banana's way to try to heat your home. So in practice, we use something that looks more like this, and this is called the vapor compression cycle. So this is kind of the simplest version of a vapor compression cycle with four components. It has a compressor, which basically does the action that the human does in that XKCD drawing of really crushing down and compressing the working fluid. It has a condenser. This is basically where the working fluid radiates energy to the indoor environment. It has an expansion valve, which in my opinion is kind of a magical component. Basically, when the working fluid flows through this valve, its pressure drops and also its temperature drops a lot. So then it becomes really, really cold here. It flows through an evaporator. This is another heat exchanger where we have an absorption of energy from the outdoor air. So we can look at the different states here. So after leaving the compressor, we have hot, high pressure vapor, high pressure gas. That flows through a condenser and we undergo a phase change and in general, typically a temperature drop. So all that high pressure vapor condenses into liquid and also cools down somewhat. We flow through the expansion valve and we get low pressure and very cold liquid. And part of the art of choosing a refrigerant to run in a heat pump cycle like this is finding something with the appropriate properties so that when it flows through an expansion valve, kind of at the temperatures and the pressures that we're using in the cycle, we get a really big temperature drop. And then we flow through the evaporator. So here we have a liquid and it's very cold. It comes into contact with, say, outdoor air or some outdoor water, something like that. And it boils in the evaporator and also typically will increase in temperature somewhat. So we're absorbing our input heat transfer QN. We have work running the compressor. There's no work, no heat transfer at the expansion valve. It's typically a passive component. And then we have a heat transfer output from the condenser. And this is, again, what we use to heat whatever it is we're trying to keep warm. Any questions about this? Yes?
Can we condense without using the compressor, run directly from low pressure?
So could we cut the compressor out of this cycle? So why we need the compressor in the cycle is basically we need to raise the temperature of the working fluid so that it is higher than whatever it is we're trying to keep warm. So you can think of this being indoor environment at maybe 20 Celsius. and outdoor environment, call it, -5 Celsius, something like that. So that -5 C it puts an upper limit on how warm the fluid could ever be, right? Um, in order to absorb energy via heat transfer, you need to be in contact with something that's warmer than you are, basically. So in order to get, something that is hot enough to give off energy, thermal energy to this 20 to 20 Celsius indoor air, we need to raise it to at least, a bit above 20 C. And so there is generally something is needed in there to do that, that temperature rise. Now, there are other ways to do heat pump cycles that are not vapor compression cycles, so that don't have compressors in them, that you can do it via chemical reactions, for example. And so, yeah, there are people who work in Herrick Laboratories. Does anybody work on alternative cycles for heat pumps? Joseph? You've heard of them, but don't work on them?
Yeah.
Okay, cool. Anyway, Zach, in your ME 500 class, did you guys learn about other
No.
chemical heating, pumping loops or anything like that? No. Okay.
Mostly stuck to
Yeah, I mean, this is like, if you buy a heat pump or an air conditioner, this is basically the technology that it uses. A few more bells and whistles, but this is the basic idea. But anyway, yeah, but also lots of research being done on other ways to do this. Yes.
Have they found it useful? Like, where does the loss go at the expansion valve? Where does losses go?
Where do the losses go
I
at
guess
the
if you're
expansion valve?
increasing It's more than pressure, you're going cold and low pressure. I would think that there'd be some losses associated with that.
Yeah, and there aren't, and that's totally weird. And that's why expansion valves and refrigerants in combination are like a totally weird invention for me. But well, I mean, so actually, yeah, so where does the energy go? It's not. So this is typically modeled as an isenthalpic device, meaning the enthalpy coming in here is equal to the enthalpy going out here. It's very weird. So there's a Carnot version of this, the sort of Carnot vapor compression cycle, which actually would have a turbine here that would produce a work output. So basically, as you are sort of losing energy here, or you imagine losing energy there, you actually get a useful work output there. But we don't typically find those components in practice because it just adds a lot more sort of complexity to the machinery, and usually the amount of work that you get out of it is not big enough to justify that. Okay. And by the way, not every fluid, if you flow it through an expansion valve, does this. It won't always drop in temperature. Some of them will actually go up in temperature. So it's very strange. So this is part of the engineering of vapor compression cycles. It's like finding the right fluids and the right design of expansion valves and things like that. Okay, and then here's kind of a slightly more realistic version of what this would look like for, say, a residential application. So you would have what's called the outdoor unit, typically, which would have the compressor and the evaporator, often in just like, they might be together in one big hunk of plastic and steel. And then the indoor unit contains the condenser, and this is the heat exchanger where we basically give off thermal energy to the indoor environment. And the expansion valve might be located outside, it might be located inside. And if you go around, just looking in backyards in West Lafayette, you will see components, basically big, outdoor units, big cubes of steel and plastic. And those are typically not for heat pumps, they're typically for air conditioners, but the equipment looks very similar in what's called a unitary residential air conditioner. Okay, so suppose that for your semester project, you want to include something about a heat pump. And you want a fairly realistic model of its coefficient of performance. We know from the building modeling section, we know how to get sort of what the demand for heat is for a particular structure. But in order to understand what the electricity usage would be from the heat pump, we need to understand the COP curve. So we talked about one way of doing that, which is to use the Carnot limit or to like take a fraction of the Carnot limit. And that can do okay, but better approach is actually to just get some empirical data from actual machines that people have built and tested. So NEEP, the Northeast Energy Efficiency Partnerships, maintains a database of air source heat pumps. So this would not get you sort of a COP curve for, say, a ground source or a geothermal heat pump. But if you're interested in an air source unit, this is a nice source of data. And I pulled some data from kind of some common units, 3 different ones from 3 different manufacturers. And here I'm plotting on the y-axis coefficient of performance, and on the x-axis the outdoor temperature. And here we're assuming that the indoor temperature is held constant. So rather than looking at that temperature ratio of T cold to T hot, we're just looking at the outdoor or T cold temperature here. So anyway, over the kind of range of outdoor temperatures that you typically see in heating applications, there's roughly a linear dependence on the outdoor temperature. And I've given you the equation of the line here. So you could just take that and put it into your model and use it to convert basically thermal energy to electrical energy. These are for what are called central ducted units, and we'll show in a minute some comparisons between different configurations. But this is kind of, if you have central AC, this is kind of the version of a heat pump that you would use with that system. All right, so to simulate a heat pump, the simple way to do it, and this is not perfect, but it's kind of quick and dirty and usually good enough for most purposes, would be to assume that the indoor temperature is approximately constant. In reality, of course, indoor temperatures change a bit, but usually they change within a pretty tight band of a couple of degrees. So that variation is not so important. What is really important is the dependence on the outdoor temperature. So we can model the COP as basically a function of, call it theta, the outdoor temperature. And then we fit a curve, and I just showed you an example of what that looks like. Basically, you could put it into Excel and just find the line of best fit, and then look at the equation of that line. And so then we fit a function eta of theta. That's basically just this. And so here I've actually used the max function, which again, max of x and y just gives you back the bigger of x and y. So I've taken the max of 1 and then the line that shows up in the plot here. So the idea is if it was super duper cold, you can extrapolate this line down. At some point, it would go below 1. But a heat pump, as long as it's operating correctly, should never go below a COP of 1. And in fact, many heat pumps will switch over to electric resistance backup heat when it's really cold outside, and then they basically just directly switch over to COP 1. So that's what the max 1 does. It basically puts a floor on the COP curve of 1. And then in the simulations that you guys did, I guess for the homework that is, or are doing maybe for the homework that's due tomorrow, we have thermostatic control, and that imagines basically switching between the minimum and the maximum capacity for the heat pump. So to do that, you might specify an electric power capacity basically for the compressor. Might be on the order of 4 or 5 kilowatts, something like that for a typical residential application. And then you would take that P max, multiply it by eta, and that would give you basically the Q max, the maximum amount of heat that you can supply to the building that shows up in the thermostatic control. Yeah. Okay, so then here's the relationship. Basically, this just comes from definition of COP. This heat transfer divided by work input. So we get P is just equal to Q divided by eta. Okay, and then I mentioned that very often we put electric resistance backup heat in alongside an air source heat pump. So the idea is that a heat pump is generally expensive to install. It's a fairly complicated machine, but it's cheap to run. It's highly efficient. And that's kind of the converse of resistance, which is cheap to install, but quite expensive to run. And so a hybrid system basically would say, okay, we need, for the worst case, coldest day, we need a lot of heating capacity. But we don't need to be super duper efficient if that only happens a few hours per year. So we can use electric resistance to help out on those bitter cold days. And then in the bulk of the year, we'll use the heat pump to heat efficiently. So here's what the electric power consumption of a hybrid heating system would look like as a function of the heat transfer Q that it's delivering to the building. So here we might have a fairly low thermal capacity from the heat pump, and that would be given by the coefficient of performance times the electrical capacity. And the slope of this line here is basically 1 over eta. And then, so that tells us that we're more efficient down here than we are up here. And then as the load increases above the capacity of the heat pump, so we're over in this region now, then we're heating basically with an efficiency of 1. And that gives us the slope of this line up here. So this whole curve, the kind of kink curve here that we have, is given by this equation, where we're just taking the larger of 2 lines. One of them is this line, right? So that's just our Q over eta. And then the other one is this line. And you can convince yourself if you use the point slope formula for a line, we've got this point here, and we know the slope is equal to 1, that would give you this linear equation. Okay, so again, you could basically take this thing. You could do building simulation to come up with what the Q, the heat demand of your building is. And then you could use this equation to say what the electricity usage of the hybrid heating plant would be. Okay, any questions about electric heating? Yep.
Does resistance heating sort of break down faster at high temperatures? Is that like once you start hitting like, I don't know,
Oh, like how high temperature can you go with resistance heating?
Yeah.
So that actually is a function of mainly of the metal that is used for the heating element. And for most applications, like the nickel chromium alloy that I think I mentioned would be used in a lot of kind of lower temperature applications, it might get up to around 1,000 degrees Celsius. But if you want really high temperatures for some industrial process, you're trying to melt some metal or boil something really quickly, whatever it might be, you might want higher temperatures than that. And so, yeah, there are people have put together kind of other materials that can be used for resistance heating. A lot of other metals and alloys, but also some non-metal materials. So I think some ceramics and some graphite, I guess, is one. And they have pros and cons in terms of how durable they are and how quickly they degrade and stuff like that. But I think you can get up to temperatures around 3,000 Celsius. I think with the graphite ones. I'm just reiterating basically Wikipedia level knowledge. So if you want more knowledge than that, go to Wikipedia and then follow the links to whatever they reference. Okay, so moving on to cooling. Well, we already have learned about heat pumps, and an air conditioner is basically just a backwards heat pump. So heat pumps often are the ones that we install, especially the air-to-air heat pumps that are very common in the US, can do both cooling and heating. And when they're cooling, they actually, will do what's called sensible cooling of reducing the temperature of the indoor air. And they can also do what's called latent cooling, meaning wringing moisture out of the indoor air. So they can dehumidify as well as cool. And this is part of the value of a heat pump or a two-way heat pump is that it basically does two jobs for one piece of equipment. So rather than needing a furnace or a boiler to do your heating and an air conditioner to do your cooling, you can put in one machine and just reverse it for cooling. Okay, so here is some vocabulary. I guess it's not strictly heat pump vocabulary. You could call it HVAC vocabulary. But basically, if we're running a refrigeration or a heat pumping cycle between two reservoirs, we might call one the heat source, the thing we're absorbing heat from, and the other is the heat sink, the thing we're delivering heat to. And then we have different names for different devices. So if we're absorbing energy from the air inside of a refrigerator and dumping it into the air in a kitchen, we call that a refrigerator. So, and this really does happen. If you pull your fridge out from the wall and you wait for the compressor to cycle on, you'll hear a click and a whir. And then you put your hand on the back of the fridge, it will feel warm. It'll feel hot. All the coils in the back of the fridge are basically the evaporator, and that's where the refrigerant gives off heat to the ambient air. If we absorb energy from the outdoor air and deliver it to the indoor air, we call that a heat pump or an air source heat pump specifically. Sometimes we would call it an air-to-air heat pump. And then if we just flip this, we absorb energy from the indoor air and dump it into the outdoor air, well, we call that an air conditioner. Or again, an air source heat pump just running backwards. If rather than absorbing energy from the air outside, we absorb it from the ground, we would call that a ground source heat pump or a geothermal heat pump. If we suck energy out of the outdoor air and dump it into water inside, typically that's called a heat pump water heater. And we'll talk about these next lecture. Heat pump water heaters can also absorb energy from the indoor air or the outdoor air, depending on whether or not they're ducted to the outside or whether they just kind of suck heat out of the, say, basement air. And then if we kind of do the opposite of a heat pump water heater, so we absorb energy from water that's inside, we're trying to cool down some water, and then we dump the heat outside, we call that a chiller. And we have huge chillers here at Purdue at the Wade Utility Plant for providing cold water and air conditioning to buildings here on campus. And then I guess if we flip that, so we're absorbing energy from water that's outside and moving it inside, you would call that a water source heat pump. And you might want to do something like a water source or a ground source heat pump. Basically, if you want to improve the efficiency of providing heat to indoor air. And the reason that that improves efficiency basically is that in really cold weather, it might be, say 5 degrees Fahrenheit outside, but if you go down maybe 10 feet underground, it might be like 40 or 50 Fahrenheit. And similarly, if you have a deep lake and you go down near the bottom of the lake, it might be 35 Fahrenheit or something like that, pretty much year round. So using that as the reservoir that you're absorbing energy from, and if we think back to that COP curve, it's going to basically move your ratio T cold to T hot to the right and move the COP up. Yes.
Does the heat pump water heater also air conditioner because it sucks heat from the indoor air?
Yeah, so the question is, if you were doing this line, sucking heat out of the indoor air and moving it into water inside, is this thing also called an air conditioner? And typically you wouldn't point to the piece of equipment in the house and say this is an air conditioner, but yes, it does provide air conditioning. And by that we mean cooling, so reducing the temperature of the air kind of surrounding it, but also potentially dehumidification. So there would be a cold coil that's outside of the, say, tank of water, and we might have moisture condensing on that coil. So and that can be valuable if you have a humid basement and you don't want mold and stuff like that to grow, bringing some moisture out of the air could be beneficial. Conversely, if you're using a heat pump water heater in this configuration in winter, you're actually air conditioning the air a little bit, and then you have to heat it back up using some other piece of equipment. So you have kind of dueling equipment, if that makes sense. Yeah, but good question. Okay, so a refrigeration cycle looks basically exactly the same as a heat pump cycle. So all of this is just a copy paste of the previous diagram. The first law balance is again the same. The main difference is the point of the machine. So here, the point of a cooling cycle is to absorb energy from the colder region. This could be the air inside of a fridge, it could be the air inside of a kitchen. And so therefore we define the coefficient of performance as the ratio of kind of the useful thing to the costly thing. And here the useful thing becomes the energy that we put into the cycle. So that's Qin divided by P. We again can use the first law to replace the P in the denominator there. And we find that the COP depends only on the ratio Qin to Q out, but that ratio now shows up in the numerator and the denominator. As opposed to for the heat pump, COP, it only showed up in the denominator. And then again, there's a second law or a Carnot performance limit that says no matter what you do with a real machine, it can never be more efficient than this number that's given on the right-hand side here, which basically, again, comes from just replacing the ratios of heats to the ratios of temperatures. And so here's what that looks like. So again, I'm plotting on the x-axis the ratio T cold to T hot, and on the y-axis, we're plotting the Carnot performance limit. And here, the limit of 0, okay, this basically means that the cold reservoir temperature is approaching absolute 0. And this says that your COP basically goes to 0. So if you're trying to cool something down that is at cryogenic temperatures, it's going to be super duper inefficient to do that cooling. And as you approach absolute 0, the amount of work needed to extract more energy basically blows up. It goes to infinity. And that's what gives us the idea that absolute 0 is sort of a limiting temperature, the lowest that we can go. Yes.
We're using the refrigeration cycle model to model air conditioning.
Mhm.
Would we have to change it based on where our compressor is located, whether it's inside the house or outside of the house? Like, because wouldn't it be kind of a parasitic load on the Qin if it's inside the house?
Yeah, so the question is, if we're using a vapor compression cycle to do air conditioning, would we have to model it differently if the compressor is inside versus outside? Because it can be kind of a parasitic load if it's inside of the house. Basically, that machine is not perfectly efficient. It's giving off heat, waste heat, and that would add to the cooling load of the house if it's inside the home. I guess so, yeah. Although I think that most of the waste heat, if the machine is designed well, should actually go into the refrigerant ideally, and then it would go to the condenser and be bled, to the outdoor air. But yeah, I don't think many air conditioners have a compressor inside, and I think it's not primarily for that issue so much as it's just like it's a rotating machine, it gets noisy, so you'd rather have it outdoors. Yeah, but it's a good question. And then we also get the same kind of blow up behavior here in the COP curve. So when the temperatures become approximately equal, we get, potentially nearly infinite COP. We can play the same game with air conditioner data. So this again is coming from that Northeast Energy Efficiency Partnerships database, which, by the way, all the teal text here is links. So if you need this for your project, you just click on this and you can download data for yourself. But here I took, three kind of different units from different manufacturers, and I'm plotting again the outdoor temperature with the assumption that the indoor temperature is held, roughly constant. And we see the dependence here is kind of linear with a negative slope. So the COP drops as it gets hotter and hotter outside. Okay, so there is one additional kind of wrinkle. I mean, there are many different wrinkles between heating and cooling, but there's one that I think is the most important to model, which is air conditioning is not just cooling things down, it's also potentially dehumidifying them. So to model the humidity effects, look, you can get very, very detailed with this. It gets complicated quickly, but there's a simple kind of quick and dirty way, and that's what I'm going to tell you about right now. So we provide what's called sensible cooling, basically reducing the indoor air temperature, and also what's called latent cooling, so condensing moisture out of the indoor air. And then the total heating demand, the total load, would be equal to the sensible load, the temperature change component, plus the latent load, the phase change component. And we define the sensible heat ratio, this thing I'm calling S, as just the ratio of the sensible load here to the total load. So if we're doing building simulation in the way that you guys are doing for the homework this week, typically we're only looking at the temperature, the sensible component of loads there. So the Q that comes out of your building simulation basically would be only the sensible component. But of course, the amount of electricity that we put in would also be a function of the other component, the condensation load. And so in order to get the total electric power consumed by an air conditioner, what we want is the total thermal load divided by the COP. And we can get that basically by generating the sensible load and then coming up with an approximation or an estimate of the sensible heat ratio S. And then we just define the total power P as Q divided by S times our COP. And in reality, this thing S is quite complicated. It's a function not only of the indoor conditions, how humid the indoor air is and so on, but also what's happening on the coil, what material it's made out of, how cold the refrigerant is, and things like that. But kind of for a typical or a plausible range, you might think kind of 70% for a humid climate. And actually you could get lower than that in a really muggy place, somewhere like Louisiana or Florida. And then all the way up to maybe close to 95% for a dry climate. So if you are air conditioning in Arizona, unless someone has just taken a really steamy shower inside and there's suddenly a lot of moisture in the indoor air, typically things will be really dry, and most of the cooling that you do will be sensible cooling. All right, so let's talk briefly about sizing heating and cooling equipment. So there are many ways to do this, and it kind of depends on the models that you're using and the equipment that you're working with. But again, I'm going to give you kind of a first cut method here. So we talked about coming up with this overall thermal resistance R between the indoor air and the outdoor air. We talked about, I guess, 2 or maybe 3 different ways of doing that. One kind of data-driven way, and then one way that looked more kind of at what are the materials and the geometry of the building, and did something closer to first principles analysis to get R. But anyway, at this point, you guys know roughly how to get R, and I think there's a problem on this week's homework about that. So we do that, and then we get what are called the design conditions. So the design indoor temperature and outdoor temperature, and you can look these up. Someone like ASHRAE or Energy Star would typically have a database of indoor and outdoor design conditions. And then this is a more challenging part, but basically pick a plausible value of the internal heat gains that shows up in the RC model for something like 4 in the morning, which is typically the coldest hours of the day, 4, 5, 6, something like that. It's kind of nice because typically in the coldest hours, there is no sunshine. So we don't have to think about the solar component of this. We mainly have to think about kind of the electrical loads, refrigerators, networking equipment, computers, body heat, stuff like that. Okay, and then basically we take our 1R1C model, we assume it's operating in steady state, so the time derivative of indoor temperature term that drops out. And then we solve it basically for Q or for P divided by eta, which is the same as Q. And so this is basically the right-hand side comes from solving that 1R1C model in steady state. And then the thing that shows up here in the numerator R is called the oversize ratio. And there's guidance basically for how much you should oversize equipment. In reality, if you look at real furnaces and boilers and things like that in people's houses, often it's 2 or more. I once lived in an apartment that had an oversize ratio of 7, meaning the heater was 700% bigger than it needed to be to meet the worst case load. So you can find just ridiculously oversized things. By the way, that apartment was like it was basically built over a garage, and I think it had really small heating load because it was a pretty small apartment, and they couldn't find a furnace small enough basically, so they just put in one for like a full size building. But anyway, 40%, 30%, something like that is typically a better guideline there. Okay, and then for cooling, same deal, but now we have S basically showing up in the denominator. And there would be a negative sign here. So we flipped, the outdoor temperature typically is higher than the indoor temperature. So we have a sign flip there. And then for cooling, specifying this thing here is actually a little more challenging because it has to do with solar heat gains as well. So typically the hottest hours of the year are on sunny afternoons. And so this QE might be, on the order of a couple of kilowatts for a normal house. All right, and then what if we're putting in one machine that we want to do double duty for both heating and cooling? So I think we start by just running the very simple algorithm that I showed in the last 2 slides to come up with what you would choose for the size of your heat pump if you were only going for heating or if you were only going for cooling. So come up basically with the peak loads for heating and cooling. And if your heat demand is below your cooling demand, so this would be in a warm climate, somewhere like Florida, then you just size the thing for cooling. So you put in, basically the air conditioner that you need in order to keep the house cool or the building cool. And then you get basically the heating capacity that comes along for free. If heating is bigger, your heating load is bigger than your cooling load. So this would be basically somewhere like in the north of the US. Indiana probably would meet this. Then we have a couple of different options. One is we could just size for heating. So put in a really big heat pump and accept that it's going to be way oversized for cooling, which might or might not be okay. Another option would be to just size for cooling, same way that we would do in a warmer climate, and then add backup heat. And there are many options of what that backup heat could be. Electric resistance is one simple option. And the amount that you have to add is given by this. Another option would be basically try to do number one, but fail because nobody makes a heat pump big enough for your demand if you're in northern Minnesota or something like that. And so then you would get basically the biggest available unit, so size it for heating, but then add some backup heat as well. And each of these options would have trade-offs. So in number one, we'd have a really efficient heating system, but it would be really big. And so it would be probably more expensive than it needs to be. For option 2 here, we would have, just a well-calibrated machine for the kind of air conditioning tasks, but it would be too small for heating. And so in a lot of cold conditions, we would have to be using backup heat, which is going to hurt efficiency. Okay, and then what could this backup heat be? Well, it could be another heat pump. So they're what are called point source or mini split heat pumps, and I'll show some illustrations of those in a little bit. So you could imagine augmenting the heat pump system with another one of those inside. It could be electric resistance. You could use some kind of thermal storage system. So if you have excess heating capacity during the day, you could imagine using it to make hot water or something like that, and then using the hot water overnight to supplement your heating system. You could have a wood stove. You can imagine having a propane backup heat, maybe furnace, something like that. Heating oil similarly, or natural gas. And there are probably other options that I haven't put on here, but basically making heat is pretty easy. Making cool is pretty hard. That's why we have backup heat, but not backup cooling. Okay, so here's an example. If we, I think I pulled some numbers that are roughly accurate for our test house near campus here. So here our outdoor design condition is -16 Celsius. By the way, to convert Celsius to Fahrenheit quickly, roughly, you can just sort of double the Celsius number and then add about 30. So this would be about 2, something like that, Fahrenheit. Indoor design condition for heating, 21. So again, double it and add 30. I don't know, about 72, something like that. And then pick a low value here. Again, this like doesn't have solar in it for heating applications. And then COP for heating on a really cold day might be, a little bit below 2, something like that for an air source heat pump. And then for the cooling design conditions, we have, I guess, over 90, maybe 90, 95, something like that, outdoor conditions, and a little bit warmer. People typically choose a little bit higher set points for cooling than they do for heating. And then we have a higher value, both of the heat gain, because this has sunlight mixed in it. And we also have a higher value of the COP. Generally, that temperature ratio between the outdoors and the indoors is a lot smaller for cooling applications than it is for heating applications. And so we can get significantly higher COPs. And then here are the parameters that I picked: the thermal resistance, just a round number, 3 degrees per kilowatt, 30% oversize ratio, and 80% sensible heat ratio. So if we run the numbers for heating, we would get about 8.2 kilowatts for the kind of electrical capacity. And for cooling, we get around 2.7. So there's like roughly a factor of 2.5, something close to 3, I guess, in between the cooling load and the heating load. So about 7.5 kilowatts, roughly, electric capacity in cold weather is pretty much the biggest heat pump that you can find for an air source unit on the market today. So even if we got kind of a huge machine, we would need some form of electric, or not necessarily electric, but some form of backup heat. All right, any questions about sizing? Yep.
So the energy consumption mainly varies because of the COP buckets, for lower COP of the heat pump.
Yeah, I guess so. The question is, how does the energy consumption vary when we're doing heating and or cooling? Yeah. Right. So it's 2 things. One, so as it gets colder outside, just the demand for heat in order to maintain comfortable indoor temperatures is going to go up. So temperature drops and thermal load basically goes up roughly linearly. So that's one reason in cold weather we would consume more energy for heating. And then the other is that the COP also drops. So you get this kind of like really nasty coincidence, which is just as your demand for heat is going up and up, your efficiency in providing that heat is going down and down. So that's why energy goes up, kind of faster than linearly, I guess, in cold temperatures. So the indoor-outdoor temperature difference, if it's 70 Fahrenheit inside on a really cold day, it might be about 0 outside. So you'd have a delta T of about 70 Fahrenheit. And so that means that your load is going to be high, and also your COP potentially is going to be low. And then for cooling, you might have, say, 75 inside, 95 outside. You've only got a 20-degree delta T. So that basically explains the roughly factor of 2 difference between the sizing for cooling and the sizing for heating. Although there's a competing effect, which is in summer for air conditioning, you also have sunlight warming up buildings, and you also have humidity effects, which add electrical demand. Make sense? All right, so I'm just going to show some pictures now of what HVAC systems look like. And we'll start with, I guess, the most common, at least in the US, system for residential buildings, which is called a central ducted system. So here we have the outdoor unit and the indoor unit. The indoor unit, I guess, would be called an air handler. I like kind of the names in HVAC are very simple. What does it do? It handles air. Okay, we'll call it an air handler. So this basically would get return air. So this is the light blue air coming back from return ducts that might be in the floor in most buildings. So we have that flowing through here. There would be typically a filter, scrub out the cat hair or whatever is in the air. And there's a blower in here, basically a fan that would push air up. And this is the indoor heat exchanger. So this would have very cold refrigerant in it, and that would cool down the air. So light blue means cool and dark blue means cold, I guess. And then that gets pushed by the blower through these ducts. And there might be, in a 2-story house, there might be like ducts that go both to the second floor from below and to the first floor from above. But they blow cold air here, and hot air rises, so the cold air is going to sink. So having the supply high would basically promote mixing in the indoor air. And then we have all the floor ducts here that would suck back the return air. And then the outdoor unit would have the compressor. I actually don't know where the expansion valve lives, if it's indoors or outdoors. But it also would have the outdoor heat exchangers. And then this is pulling in, cool-ish or outdoor air and then exhausting hot outdoor air. And if you walk, by the outdoor unit of a window air conditioner, for example, you'll put your hand near it, it'll feel hot. Okay, so that's the central system. This is what's called a ductless mini split system. I mentioned this. This is what people sometimes call point source heating or cooling. So rather than having kind of a central plant that then pushes conditioned air or water around the whole house, you would have just kind of one unit paired with one indoor unit here. So the outdoor unit in this case has the compressor, the outdoor heat exchanger, probably the expansion valve, and this thing would be powered outdoors. And then the white run here is refrigerant lines. So it would basically supply refrigerant to a heat exchanger here in the indoor unit. So if we're doing air conditioning, we would have cold refrigerant flowing in, and then there would be a fan here that would blow, basically suck in air and blow it over that coil. And then hot refrigerant would return back to the outdoor unit. That's for both of those, I guess you would call forced air or air-based distribution, but we can also do water-based distribution. So does anybody have radiators in their current place? A couple people, yeah. So here's what that might look like. Again, drawn with a heat pump, but we could just as well insert a boiler, fossil fuel boiler in here. But basically the heat pump would supply hot water and it could be used for various purposes inside. It could pipe directly into radiators, provide space heating, and then you'd have return water coming back out. Sometimes you'd have one piece of equipment that would provide hot water both for space heating, but also for domestic hot water uses, showers, baths, dishwashing, things like that. So you could imagine running some of the hot water into a tank, which then could feed showers and baths. And then this isn't very common in the US, but I guess in European buildings, this is more common to have underfloor or kind of a slab heat, where you'd have a heat exchanger actually in maybe the concrete floor, and then you'd get kind of nice radiant heat coming from below. Yep.
I've heard a lot about those types of systems with radiant heat. Are they more efficient depending on the climate? Like, because I think if it worked really well, then we'd have it here as well. But
yeah, so the question is, are these sort of radiant heating systems more efficient? And the answer, I think, is not in general, not necessarily. One thing that they have that most US systems don't have is they have a lot of thermal inertia, a lot of thermal mass. So you'd heat up like this big block thing here. And so you could imagine that leading to a lower cost, although not necessarily lower energy system. If you could heat up all that thermal mass when electricity is cheap, and then do less heating, but still get a lot of radiant exchange when electricity is expensive, then it might lead to a cheaper system. But I think people who really like these radiant systems, I think they typically, it's a different way, a different means of comfort delivery. So rather than in forced air system, like just blowing lots of gusts of hot, dry air on people, you'd have just sort of warm surfaces all around, right? It's kind of nice. Okay. Okay, so those are residential type systems. Here is what a typical commercial system might look like, at least in a fairly modern office building. So these are what are called variable air volume systems. And they typically have both kind of a central plant and then a number of distributed units called VAV boxes, or variable air volume boxes. But let's start at the central plant, which again would be the air handler, or the air handling unit, AHU. So here we would basically suck return air out of thermal zones, rooms, that would mix to some degree with outdoor air. And then that mixed air would run through a filter, again, to scrub out whatever particles might be in it from indoors. It would run, if we're in air conditioning mode, over a cooling coil. So here we would have cold refrigerant that would bring some moisture out of the air as well as cooling it down. And then that cold, dry air would get supplied through ducts to a number of different floors and rooms. And at each of the zones, we would have kind of our own VAV box. and I'll show a schematic of what's in there. But basically, there is a damper, a motorized damper that determines how much air the zone gets. And there's also typically a hot water or sometimes electric resistance, but there's basically a reheat device in there that can warm the air up. If 55 is too cold for what the zone needs, it can warm the air up inside. So not pictured here would be exhaust air. Typically, this is a balanced system. So as much outdoor air as we're bringing in, we would exhaust a similar amount of either the return air or the mixed air. And then this is what it looks like kind of inside this component here. So let's blow that up and see what that looks like. So it gets the cold, dry supply air from the air handler. And then again, there's a motorized damper here with a controller on it, which is getting a measurement of the indoor temperature. And also other things typically like maybe the CO2 level inside of a room. We talked about that with this room specifically, how if we have a bunch of people exhaling repeatedly, that CO2 levels can build up and that can lead to, you know, feeling of fatigue and stuff like that. So that's one of the reasons that in the air handler here, we mix in outdoor air is basically to dilute the concentration of CO2 that's coming back from the return air. And actually, CO2 concentration is a pretty good proxy for a number of other things. You can use it for occupancy. So if you have high CO2 coming back from a room, you could probably infer that the room is fairly highly occupied. You can also use it as a proxy for like pathogen count. So if you're looking at the viral load, people who were working on ventilation systems for coming back to work after COVID pandemic, right? It's expensive to try to put in an actual sensor that measures, you know, what the concentration of COVID virus particles is. But, you know, where did it come from? Okay, it comes from us exhaling. And so if you measure the amount of exhale, basically the amount of CO2, you get a reasonable estimate, I guess, of the potential viral load. Anyway, so this thing would determine based on, you know, air quality as well as temperature needs, how much air to blow in. And then based on essentially the thermal needs, you decide how much hot water. Typically, this is a hot water system. Sometimes it would have an electric resistor in it, but how much water basically to flow through there. Okay. So those are some schematics of what thermal distribution equipment can actually look like in buildings. Let's talk a little bit about modeling some of the devices that show up there. So here is an example of a forced air heating system. So we're imagining we just have one thermal zone, or maybe it's a residential building, a house, something like that. So here I'm doing kind of an energy balance around the control volume that is the indoor air and thermal mass. So we would have you know, some exogenous heat transfer coming in from sunlight, from body heat, whatever it might be. We might be bleeding some heat to the surroundings through conduction through the walls. And then we would have the kind of intentional heat transfer happening, where we would be putting in mass flow rate m dot at some supply temperature. And then the air would mix and we get back typically in a balanced system. We're not like blowing up a balloon, you know, putting tons of air inside. We'd get basically the same mass flow rate coming back out. And then the return temperature would be roughly the mixed air temperature inside of the room. And so here m dot is the mass flow rate in kilograms per second, or, you know, mass per time units of the supply air that we're sending into the zone. So if we do a first law balance on this thing, we get basically the 1R, 1C model. So we have C times our indoor temperature, time derivative, is equal to basically the delta T term here, plus, and this QC is what shows up in our RC models. So this is the net heat supply from kind of the intentional heating that we're doing via mechanical systems. So this has to do, this is basically the enthalpy change formula for an ideal gas. So air at kind of normal temperatures, ambient temperatures is well modeled as an ideal gas. So we get basically an m dot Cp delta T, where the delta T is between the supply and the return temperature. So that is our intentional or controlled thermal power, and then we have the exogenous term here as well. And then Cp that shows up here is called the specific heat at constant pressure of air, which is about 1 kilojoule per kilogram degrees Celsius. Okay. So that is kind of our model for forced air heat transfer. We can also talk about hydronic or water-based heat transfer. Here, same basic schematic. We have the same kind of MDOT here, but rather than talking about the air being pushed into a zone, we'd be talking about the water that's, for example, flowing through the radiators in the back of this room. So we can again do our power balance, and we get now using the incompressible substance model, right? So water is well modeled as incompressible, basically constant density at sort of ambient temperatures and pressures. And so we get another m dot c delta T turn here, where the delta T is basically the difference between the supply and the return temperatures. And then C, the specific heat that shows up here, you may remember from your undergraduate classes, an incompressible substance only has one specific heat, whereas something like a gas would have a specific heat at constant pressure and a specific heat at constant volume. So C is the one and only specific heat of water, which at kind of standard temperatures and pressures is about 4.2 in these units. Okay, and then we might want to know, in addition to what the heat transfer term is that should show up in the RC model, we might also want to know how much energy our pump or our fan is going to be using for basically pushing around the heat delivery medium, the working fluid. So for a fan, we can do a power balance on the fan. Basically, it pulls in, if it's operating in steady state, a given mass flow rate m dot, and it would push out the same mass flow rate. The temperature of the air in general might increase over the fan. And then we're putting in this work here. So we can do a power balance here. It's not exact, but it gives a rough estimate of the fan power. That would just be the m dot Cp, and then it would be the temperature delta again across the fan. For a pump, the enthalpy change formula for an incompressible substance would have not only the temperature change component, but it would also have potentially a pressure change component. So the water pressure downstream of the pump might be a little higher than the water pressure upstream. And so if we do a delta pressure divided by the density of water, we would get basically that contribution to the overall power consumption. And so here rho is just density of water, and it's about 1,000 kilograms per cubic meter. Okay, so these are kind of quick and dirty formulas that are based on a first law conservation of energy type balance, and stylized models of gases or liquids. In practice, sometimes we use that. Sometimes we'd use something that's called an affinity law. So if you do kind of kinetic modeling, I guess, of say air flowing through a fan, you find that the electric power, the work input to the fan, is proportional with some constant alpha to the mass flow rate cubed. So we get roughly cubic power dependence. And here the coefficient alpha, typically you can find a fan if you can find its model number. You can pull manufacturer spec sheets, and you can look up kind of under rated conditions, which would be basically a rated airflow. You can find the rated electric power consumption. And that's something that the manufacturer would measure probably in their own laboratory. So if you take the ratio of those two, that becomes the coefficient alpha that shows up in this formula. But more often in practice, what we would do, if you wanted to characterize an actual fan that you're trying to control well, you might just run it through some different conditions, different airflows, and just measure the electric power consumption. And that would give you a data set of airflow and power. And then you fit essentially an input-output model to that data set. And that might take the form of a polynomial where you would keep not just the cubic term that shows up in what's called the fan affinity law, but it would also have the quadratic, the linear, and the constant terms. And we'll talk a little bit later in the semester about how you would fit, find the numbers to use for these parameters. This is called a regression problem. But you could do it in Excel. They're very fairly easy to use tools that can help with these fits. So that's all that I wanted to talk about today in terms of HVAC equipment. I guess we have 10 minutes left. Let me just run through, I guess, the assignment of the homework really quick. So first of all, homework 4, which is due not this Wednesday, but next week, Wednesday, is up, so you can read through it. And it has, as usual, some kind of pencil and paper problems, and it has a coding problem. So let me zoom in a bit. Okay, so problem one is, this is the pencil and paper thing. Basically, I skipped some steps in one of the derivations of kind of the governing equations for a thermal storage system. And I will present those, that model, or not tomorrow, on Thursday of this week. And so basically there's just some blank stuff that you will fill in. So it's, I think, 5 or 6 missing steps of math. Not too hard, hopefully. Problem two is a little bit more involved. So I think this whole problem is 50% of the points on this problem set. But this basically walks us through basically comparisons between heating with electricity versus heating with natural gas. And in particular, it takes into account an often neglected consideration when doing these comparisons, which is the fact that natural gas infrastructure leaks methane, which is the principal component of natural gas. Typically 90% or more of natural gas when it's delivered to pipelines is methane. And methane is actually a very potent greenhouse gas. So much more potent than CO2 in terms of its warming effect. So basically, there's simple comparisons that you can do where you neglect the methane emissions from natural gas infrastructure. But if you take into account the methane emissions, then the comparison actually changes quite significantly. So this question basically walks you through how to model gas heating systems, electric heating systems, and then walks you through some comparisons of the two. And then the coding problem for next week is related to water heaters. And again, we haven't talked about this, but we will talk about it. Water heaters are basically thermal storage systems, and so we'll talk about them on Thursday in the thermal storage lecture. So we'll go through, a little bit of code. I think I won't go through it today, but maybe on Thursday I'll go through it a little bit. And then I just wanted to draw your attention to the fourth problem here, which, again, I'm just trying to give you kind of incremental deadlines on your project things so that you guys can find topics, find literature, find teammates, and things like that. So here, basically, I want you, you don't have to have read any literature. I'm not going to ask you for like a written synthesis of a report, which you could generate with ChatGPT in about 4 seconds. But I'm just going to ask you basically to go through, and for each team member to tell me a reference that you will read, at least one. You can do more than one if you want to, but at least one for each team member. And then my thinking is that each team member would be like sort of take the lead on one of the references. It doesn't mean that they're the only one who would read that. Of course, you guys can cross-pollinate ideas and things like that. But they basically would lead a review of that. So here, basically what I would like you guys to read is things that come from fairly reputable sources. So I don't want like a Wikipedia page. I don't want a random report from like some company that's like, my product is so great, and I'm going to tell you why. We want something that comes from a fairly neutral, kind of independent source. Something like a government agency, a national laboratory. So the National Renewable Energy Laboratory, NREL, has a lot of reports on topics related to DERs. Other national labs do as well, Lawrence Berkeley, Oak Ridge, and others. And then there's a whole lot of academic work that you can find. So if you just pull up Google Scholar, for example, and you search, solar plus storage residential, something like this, right? Suppose that that's the topics that you guys are excited about. You can find a functionally infinite list of papers that people have written on related topics. So you'll probably need to get more specific than this. You'll probably need to put in technoeconomics or something like that if you're interested in kind of looking at the payback time of installing a system like this. But the idea is that you want to find something that comes from a reputable source, something fairly recent. So you probably don't want something from before the turn of the century, but the last decade or so, I think would be good. And so that's another way that you can find these sources. And that's all. I think the coding problem is, I feel like last week's coding problem, that policy number 3 for EV charging, was like way too hard. So I apologize for time that you guys may have spent on that. Next year, I might move it back to extra credit. But I think compared to that, both this week's and next week's coding problem should be a lot easier. Okay, so any questions about either today's material or logistics? Yes?
This week's coding question. Like part one asks us to fill in the blanks in the main file, regarding just the generalized matrices
Mhm.
A and B that are used.
Mhm.
Were you intending just for us to fill in the matrices or also to plug in the discretized equation as well? I just didn't see where it would be used if we would put it there, but I saw that A and B are used somewhere else.
Okay, so the question for folks online is in the homework that is due tomorrow, in the buildings homework, we are asked in one of the parts to fill in, let's see, it's probably in the sort of wrapper script, the simulate 2R2C. We are asked to fill in some matrices here, right?
Just the matrices?
Yeah. So the answer is basically yes. So you should fill here. So the continuous time matrices would come from basically writing down the differential equations, the 2R2, or finding them in the slides, right? The 2R2C differential equations. So one has to do with the indoor air temperature, one has to do with the thermal mass temperature. And then basically writing those in sort of a matrix vector form. So that would tell you what the continuous time matrices are. And then once you have those, you should basically have fairly simple formulas. I think we may have already done related formulas in past homeworks, but that convert essentially the continuous time matrices into the discrete time matrices. So that would be using, for example, the matrix exponential. You could also use a MATLAB or a Python built-in function, C2D, continuous to discrete, for linear systems. Did that address your question? And then, yeah, the matrices that you define here will be used, I believe, as inputs to the later functions that you design. Yeah, exactly. So you should call the discrete time matrices A and B. And those are what get passed to the perfect tracking control and to the thermostatic control. And the reason for that is that when we do simulation of a dynamical system on a computer, usually we use a discrete time model. And so the A and the B basically encode the physics that gets simulated here. Okay, other questions or comments? All right, then I think we will wrap up there and I'll see you guys on Thursday.